Welcome to the Mineral Notes. Again, these notes are here for you. You can use them to help you study for a test, or you can use them if you were absent from class and you need to get caught up on the notes. Now, one of the first things I want to talk about is why we need minerals. Well, when we look at all these different things, whether it's from energy to construction to agriculture to communications, transportation, national defense, at home, at work, at play, at school, no matter where we go, we require minerals. For example, this is a neat picture. It says here, every American born will need 3.5 million pounds of minerals, metals, and fuels in a lifetime. So when we look at some of these, for example, we see salt right here. In your lifetime, you will need approximately 29,530 pounds of salt. That's a lot of salt. Where do we get all this salt? Yeah, we're going to eat some of it. But some of it's, remember, we're in Wisconsin, so we have icy roads in winter. What do? They put salt down on the roads. You might say, well, I don't use that. But part of that is attributed to you because you do use the roads. Your families use the roads. So a lot of these things that you see here, you don't use directly, but you use indirectly. When we look at something as simple as a pencil, you might say, what does this have to do with minerals? But, well, let's just start out. Let's read the first sentence. The cedar wood is from the forest in California and Oregon. Then the graphite, remember it's not lead, might come from Montana or Mexico and is reinforced with clays from Kentucky and Georgia. So we're already starting to talk about minerals like graphite. And then we move on. We see things like pumice. We see things like copper, zinc, aluminum, brass. So even something as simple as a pencil would not be possible without minerals. Something like a light bulb to make the filaments, to make the glass, would not be possible without minerals. So what is a mineral? Well, a mineral is a naturally occurring inorganic compound or element found in the earth. And a mineral, by definition, must satisfy 5 conditions. So when we take a look at that definition, a naturally occurring inorganic compound or element found in the earth, what does that mean? Well, the 5 conditions explain it. 1, it must be inorganic. In other words, it's not going to be living. Things that make up minerals were never alive. For example, diamond and coal. If we compare these two, they're both made out of carbon. But one of these are made up of carbon that was once alive. Do you know which one it is? If you guess coal, you're right. Coal is not a mineral because coal came from plants that died a long time ago. Another condition, it must be naturally occurring. In other words, it's going to appear naturally on Earth. We're not going to man-make them. Now, we can make a lot of substances, but technically it wouldn't be considered a mineral. It must be a solid element or compound. Some minerals, you're going to find out, are just simply elements. A lot of minerals, though, are made up of a combination of elements called compounds. Another condition is it must have a definite composition. In other words, the composition, say for gold, is going to be gold no matter where it is. You can't have a composition for gold being one thing here in the United States and then being something else in China. Gold is gold no matter where you go. And the last one, 5, it must have a regular internal crystal structure. All these minerals are going to have a crystal structure. And so you're going to see that. And it must be a regular internal crystal structure. It's not going to change. It's not going to be different in other places, no matter where you go. And they can't form liquids. Now, it doesn't mean we can't melt it, but typically you're not going to find a mineral that is just a liquid. Now, how do minerals form? First of all, from cooling magma. Deep inside the Earth, a lot of the Earth's crust is melting. As one plate plows down underneath another, it's going to melt. And that magma may come back up to the surface, and as it cools, it's forming new minerals. And the minerals it forms, it really depends on, the lava composition, where it's cooling, the rate at which it's cooling. Also, when minerals are dissolved in a liquid and the liquid evaporates. For example, here, this is something that you might see out in Mount Rushmore, not Mount Rushmore, but Yellowstone National Park. So as this hot liquid comes out, eventually the liquid evaporates away. But all the minerals that were dissolved in the water have now been left behind. Now there's 90 to 92 naturally occurring elements on the Earth. But out of those 90 to 92 naturally occurring elements, only 8 of them make up 98% of the minerals on the Earth's crust. And that's amazing. There's a lot of minerals, but most of them we don't see. or most of them we see very little of. Only 8 of them make up over 98% of the minerals on the Earth's crust. Anybody know the very top one on that list? If you guess oxygen, you're right. Oxygen makes up almost half of the minerals by weight, half of the elements by weight. So you might think that's kind of odd. Why is that odd? Well, think about it. Oxygen is a gas, but it's actually one of the most, by weight, it is the most common element in the Earth's crust. And so I think that's kind of amazing. And then you put the two together with oxygen and silicon. Wow, that's a very high amount, almost 75% of the Earth's crust. And if you put oxygen and silicon together, you get something called silicon dioxide. And that's actually sand. So you've played with it as a kid, you've used it all the time. It's used to make things like windows. Other elements that we have are aluminum, iron, calcium, sodium, potassium, and magnesium. And combined, they make up about 98.5% of the Earth's crust by weight. Now, how many minerals are there? Well, there's going to be various numbers. In fact, this may change day to day to day because someone might discover a new minerals. Now, there's more than 4,000 minerals that have been discovered. Unfortunately for geologists, though, only about 100 or so of these are really abundant. In fact, we could probably break it down to about 30 minerals being really super abundant on our planet, which is good. Can you imagine if you were a geologist and you studied minerals, how long it would take you to learn 4,000 minerals and be able to identify them all? So fortunately, most of them aren't that common, and you don't see them around too often. Now, how do we identify these minerals, if you did have to identify them? Well, one, geologists will use physical properties of a mineral to identify it. These properties include things such as color, streak, luster, cleavage, specific gravity, and hardness. And several properties must be used together to determine the proper mineral identification. So most minerals you can't just look at and say, oh, that's what it is. It usually takes several of these physical properties to figure out exactly what it is. Now, there might be a few really common ones that you can look at and know exactly what it is right away, but most of them, remember, there's over 4,000. Most of them you're going to have to use multiple properties, several different properties to figure out what it is. And what is a property? It's simply a characteristic of a mineral. For example, the quickest way to identify a mineral is simply by its appearance and feel. There's some minerals you just look at, you feel them, and you know what they are. And these are probably going to be those most common minerals. But it's not always the best way. For example, we can also use something called luster. Luster is a property of a mineral that tells how the mineral reflects light. And we're going to use two common phrases here in class. We're going to use metallic. These metallic minerals shine like a metal, while non-metallic minerals vary greatly in their appearance. So when we talk about luster, we're going to mostly talk about it either being metallic or non-metallic. Is it shiny? Is it not shiny? Now, when we get into luster, yes, there's metallic, there's non-metallic, but we can also get into things like pearly, greasy, earthy. There's lots of different descriptors, but we're not going to get that detailed. We're either going to have metallic or non-metallic here in class. We can also look at the color. While color is the easiest of the properties to see, it's not always the best way to identify a mineral. Many minerals have more than one color because of their impurities. In other words, when they're out and they're being exposed to the atmosphere, they may change color. They may be different colors. So even though color is a good way to identify it, and it's pretty easy, it's not always the best way to identify a mineral. A streak sometimes would be the best way, or at least a better way than telling or identifying a mineral other than color. So a better determinant of the true color of a mineral is its streak. Streak is a test used by geologists to see the color of the mineral under the top layer. And what they will do with this is they will take a mineral and they can rub it across. And what they're rubbing across here is something called a streak plate. Now, a lot of times if you don't have a streak plate, you can just take a piece of tile and turn the tile over and use the back of the tile, the unglazed part of the tile, and just take the mineral and scrape it across here a couple times. You know, there are some minerals such as hematite. Hematite may appear red, it may appear dark brown in color, but if you put it across a streak plate, it will always be red. No matter what color it is on the surface, its streak will always be red. You could also use hardness to identify minerals. In 1822, a German scientist by the name of Friedrich Mohs set up a scale to determine the approximate hardness of minerals. He called his scale the Mohs Hardness Scale, which is kind of neat. It's named after him. And he arranged the minerals in a scale from the softest 1, which is talc, to the hardest 10, which is diamond. And the minerals get increasingly harder as you read down the scale, but they do not increase in hardness at a constant rate. So here's Mohs Hardness Scale: talc, gypsum, calcite, fluorite, apatite, microcline, quartz, topaz, corundum, diamond. When you look at number 6, that will change from time to time. Sometimes I've seen orthoclase for that. I've seen feldspar for number 6 as well. And the way it works is you can see different things in here. For example, you see a fingernail. You see a copper coin. A copper coin is going to be somewhere between a 3 and a 4. You got a knife, the steel part of it. You got glass. You have a steel tool right here. And the neat thing about it is you can use these simple devices to help you figure out what the hardness is. For example, if I had a mineral and if I could scratch it with my fingernail, I know it's automatically going to have a hardness of 1 and 2. If I had a mineral and I could not scratch it with my fingernail, but I could scratch it with a copper coin, now I've narrowed it down to having a hardness of 3. So if you can think about there being thousands of different minerals out there, there's thousands of different minerals. So if I can narrow the hardness down to, say, a 3 or a 1 or a 2, that will greatly reduce the options I have and allow me to identify it much faster. So what did I mean by the hardness doesn't go up at a set rate? If we look at diamond, the hardest mineral here, diamond is way, way, way harder than your corundum and your topaz and these ones in here. So even though talc is the softest, and it kind of goes up at a steady rate, once you get into corundum, topaz, corundum, it's a little bit higher corundum is than topaz, but wow, look at this, diamond really takes off. So let's look at it. Here's talc, here's a piece of gypsum, calcite, fluorite, apatite, feldspar, so again, this is number 6, could be orthoclase as well, quartz, topaz, corundum, and diamond. That's actually a raw diamond. You might look at that. That doesn't look like my diamond ring. Well, this is what diamonds actually look like when they come out of the ground. Another way to identify minerals is by looking at the cleavage or fracture. Some minerals have a tendency to split or crack along parallel or flat planes. These planes along which the mineral break are called cleavage planes. If the mineral splits easily along these planes, and the minerals then said to have perfect cleavage. So there's some minerals that if you snap them, if you break them, it's a smooth surface. These types of minerals have cleavage. Fracture is the opposite. If you snap a mineral and it's a jagged edge, it's said to have fracture. Fracture occurs when a mineral breaks at random lines instead of at consistent cleavage planes. Many minerals that have no cleavage or poor cleavage they fracture easily. So many minerals that have no cleavage or poor cleavage fracture really easily. They'll break. Something like talc would have fracture. And what I want to finish off with is just taking a look at a couple special properties. For example, some minerals are magnetic. For example, magnetite, sometimes called lodestone. It is magnetic. So if we had a magnet, we could put the magnet right up to it, and the magnet would actually stick to that mineral. We could also look at things such as halite. Halite has a unique taste. So if we were to take a look at halite, if we were to lick it, and I don't suggest you do this, it would taste like salt. So it's one way to identify halite. Double refraction. Calcite's going to have double refraction. If we take a look at it, when you look through it, you'd actually see 2 of everything. Everything's slightly offset. And then hydrochloric acid will react with certain minerals such as calcite. The carbonate-bearing minerals in them will react to the hydrochloric acid. And then some smell. Some minerals, if you scratch them, they'll have some sulfur in it, and you're going to definitely be able to smell that sulfur, and that's a characteristic that you can identify some minerals with. Well, I thank you for going through these notes, and hopefully these notes help you fill in your fill-in-the-blank notes for class. Hopefully they'll help you with your minerals reading questions, and most importantly, hopefully it'll help you with your test. Again, as always, if you have any questions, just please contact your science teacher. Thank you.